Okay, today we are going to talk about the general information about the photovoltaic cell, which is called by solar cell. So there are many different solar cell types, including organic solar cells, as well as the crystalline silicon solar cell, and so on. But today our main focus is general concept of the solar cells, and thereby we are going to mainly focus on the silicon-based solar cell. So let me move on to this. So as you can see, so this figure shows the efficiency versus year. So depending on, as time goes by, how the efficiency of each solar cell type has been developed with, and how much efficiency has been achieved for each solar cell. And if we look into where is it? If we look at the red one, okay, there are many different solar cells, but I couldn't find out silicon here. So red one is like dye-sensitized solar cells or organic material based on the solar cells. But many of the solar cells, with purple colors, have very high efficiency as compared with the other different solar cells. So, and those high efficiencies have been achieved by crystalline-based solar cells, such as silicon or multicrystalline, as well as the multi-junction or silicon single-junction gallium arsenide silicon arsenide solar cells. So let's move on to the. And if you look at this slide, you can easily see the solar panel that you can find from many places nowadays. So this solar panel has the role of the absorption of the solar energy, and then convert the solar energy into the electric energy. So, okay, now it is just the concept of the p-n junction. So the solar cell has the, in particular, the silicon-based crystalline solar cell has p-n junction, and all the detailed process or mechanism is performed in the p-n junction. So the details of the p-n junction will be described in the next later. Okay, so let's move on to here. So basically, the silicon has the intrinsic property in terms of the energy diagram. So if you look at the picture on the left side, then there is a valence band and conduction band. So the valence band is the maximum energy level in which the electrons can be found. Okay, but conduction band is the energy level, the lowest energy level that can be there, in which any electron cannot be found. Okay, and the energy band gap is defined by the difference between EC and EV, which is conduction band and the valence band. And EF means the Fermi level, and present between the EC and EV, which is conduction band and valence band. So intrinsic silicon has this energy diagram, and thereby there is no so the number of the electrons will be the same as the number of the holes. Okay, but let's silicon, so intrinsic silicon has no like impurity or dopant, but there is the other two types of the silicon, which is N-type and P-type. So N-type is the negative type, which is the silicon developed by the dopant of phosphorus. So once the phosphorus is inserted into the silicon crystal structures, then one more electron. So let's say we have one dopant of the phosphorus, then we have one more electron will be inserted, and thereby the number of the electrons will be higher than the number of the holes. So since the number of the electrons is increased, and thereby the Fermi level will be increased, because the Fermi level defines the level that we can find electron with half probability. Okay, so since the N-type has the more electrons, and thereby the possibility will be increased, and thereby EF, which is Fermi level, will be increased. On the other hand, if P-type, silicon is generated by the dopant of boron incorporated or inserted into the silicon crystal structure. Since the boron has lower number of the electrons than the silicon, and thereby the number of electrons will be decreased. In other words, the number of holes. So hole is the opposite concept of the electron. So if electron, okay, so electron is sort of negative charge, but hole is sort of positive charge. So by inserting the boron, we will have more number of holes and less number of electrons. Okay, so one boron insertion will generate one hole, and two boron insertions will generate two holes in this way. So since the number of electrons will be decreased, and thereby EF, which is Fermi level, which means the energy level in which the electrons can be found with half possibility, will be decreased by the same logic as I explained in the N-type silicon. Okay. So in this way, intrinsic silicon can be converted into N-type or P-type depending on the inserted dopant. So focus is N-type is phosphorus insertion, and P-type is boron insertion. So as I mentioned in the previous slide, Fermi level defines this. So Fermi level is defined by the function f, which is described here, but I will not discuss in details about the equation. But the main concept is that in Fermi level, we can find electrons with half possibility. Okay. So if we try to find electron 10 times, then 5 times we can find electrons. That is why F is half in Fermi level. Okay, you can see here. At the Fermi level, the F, which is the possibility, will be half. But energy, if the energy is lower than Fermi level, at 0K, the possibility will be 1. And the energy, if the energy is higher than Fermi level, then the possibility of of finding electrons will be 0. Okay, so that is the thing that I explained previously. So as I said, the intrinsic semiconductor, which is mainly focusing on the silicon, so intrinsic silicon will have the same number of the electrons and holes. So here, the number of the electrons and the number of the holes will be the same each other. But N-type silicon, the number of the electrons will be increased and thereby higher than the number of the hole, which is P0. Okay, but P-type, if you look at the P-type semiconductor, which is like silicon, the number of the holes, which is P0, will be much higher than the number of the electrons. So the difference between the number of holes and electrons will rely on the number of dopants inserted into the crystal structure. So if we add more number of the dopants, like in case of P-type, like if we add more number of the boron atoms, then the difference between the number of the holes and electrons will be bigger. So previously we learned about the P-type and N-type semiconductor. Then, what is the p-n junction? Like, let's say we have the intrinsic silicon. Then if we add the dopant, then we can make P-type and N-type semiconductor depending on the type of the dopant. And if we like make a junction between, make a contact between the P-type and N-type, then there would be a region showing the interface between the P-type and N-type. That is the P-N junction. Okay. So that is the basic information about the p-n junction, concept of the p-n junction. And the p-n junction is the very important concept in the solar cell because all the detailed mechanism will be happening in the p-n junction. Okay, so let me explain details. Okay, here, as I said, there is a N-type here and the P-type here. If we make the contact between the N-type and P-type, then there will be the junction, like interface, p-n junction, will be here. So in bulk phase of the N-type and P-type, they will have their own energy diagram in equilibrium. But in the p-n junction, since the energy diagram is different, because if we look at this, you can see the energy level, which is Fermi energy level, is different between N-type and P-type, right? And thereby, if we make p-n junction, then energy diagram will become like this because we have to have Fermi level constant. We have to make the Fermi level constant through the whole system, and thereby we have different energy variation like this. Okay, so in N-type we can have more electrons and thereby but while P-type has more holes here, and based on this slope, okay, we can generate built-in electric field. Like, okay, let me move on to here. Okay, let me explain the mechanism of the solar cell here. So once N-type, the excess electron, since the number of electrons are more than N-type, okay, the number of electrons in N-type is higher than that of P-type, and thereby electron has to be diffused to the P-type. On the other hand, hole will be diffused from P-type to the N-type because the concentration of the holes will be higher in P-type than the N-type. And this diffusion will generate positive charge, like in N-type in the place of the original electrons. Can you understand this part? Okay, let me draw it here. Okay, so we have P-type and N-type, and N-type semiconductor will have excessive number of electrons. So let's say electron is here. But P-type has excessive number of holes here. So based on the deviation of the concentration for each of the electrons and holes, electron will be moved to the P-type. On the other hand, hole will be moved to the N-type. Then, this is electron. This is hole. And if electron is moved to here, then in this place, where is it? Plus charge will be remained because electron, it has some sort of minus sign, and thereby to neutralize this place, this one will have positive charge. It's not the whole, like positive charge. Okay. In the same way, since hole is moved from here to there, in this region, negative charge will be placed. And we call this, so this minus and plus is a space charge, called by space charge. And this region is called by depletion. Or space charge region. And these plus and minus space charges are not be able to move. On the other hand, electrons and holes. So these space charges will make electric field in this way. So this is electric field. And we call this built-in electric field. Okay, can you understand this part? Do you have any? Okay, please let me know if you don't understand this part. Okay. And built-in electric field, the magnitude of the built-in electric field can be defined by this, the energy difference, which is QV. Okay, so this is the electric field built by space charges. And now let's say, let's say we have solar light, and if this PN junction based solar cell absorb the solar light from solar spectrum, then okay, let me explain here. So if we so electrons are in the valence band here, and if we observe the solar light, then the energy generated by the solar light will allow the electrons to be excited to the conduction band. Okay, and the electron excited from valence band to the conduction band will move to the n-type. Okay, so let's say we have electrons here generated by excited electrons here. Let's say we have one electron, excited electron here, generated by solar light. Then electron will be moved to the n-type because it has positive charge. And we can also say, based on this energy barrier, energy difference, we can easily expect the electron move from p-type to the n-type, right? On the other hand, opposite direction will be happen for the hole here. So hole, in case of the hole tend to move from lower energy to the higher energy, and thereby hole is moved to the p-type. The hole is moved to the p-type, and electron moved to the n-type. And if I finalize the whole mechanism here, then moved electron will be circulated through the external circuit to generate electricity. Okay, that is the whole general mechanism for the solar cell. Okay, here, so who of the rest parts are related to this concept? Okay, so let me move on to this. So basically, electron can so excited electron. So electron can be excited because solar light has the energy, right? The energy of the solar light allow the electron have excited. The energy of the solar light. I repeat this because it is very important. Okay, the solar light has sort of energy, right? And that energy allows the electron. Electron is generally exists in this area, which is, if we move on to here, all the electrons are here or here, with half possibility. So electrons can be excited to the conduction band if we obtain the energy higher than this difference. If we obtain the energy lower than this difference, then the electron cannot be excited. And detailed equations are here, but I'll skip, as I said. And okay, here. So let me move on to here. Okay, all the details are explained. So basically, electron cannot be moved to the area with higher energy. So in order to move electron from here to there, we need to have energy obtained from somewhere. So energy should be higher than this difference, which is built-in electric field-based energy. Okay, let me move on to here. So all the details are, so this is just experimental measurement performed by the author of the slide, but I'll skip this. Okay, so the detailed information are here, but I already explained here. So let me explain one more time. So energy here. So energy is the solar generated, obtained by solar light. Is a form of this equation. So H is Planck constant, and the C is the light speed. Lambda is the wavelength of the solar light, and mu is the frequency of the solar light. So depending on the spectrum, we can have different number of lambda and mu, and thereby energy will be changed. Okay. So if this energy, as you can see here, energy, okay, let me explain here. Energy is higher than Eg, which is the energy difference between conduction band and valence band. Then this energy allows the electron to be excited. Okay, now then let's think about the solar spectrum here. So basically, if we use UV machine, then we can measure the solar spectrum, as you can see from this. So solar light has this kind of solar spectrum. So this is solar irradiance as a function of the wavelength. So there is the visible light between 400 and 700 nanometer, and lower than 400 we will have the ultraviolet, and the higher than 700 we will have the infrared. So as you can see, the visible light region has a bunch of energy area here. So the area lies on the how can I say? the so area means the amount of the energy that we can have from solar spectrum. So it is important that the solar cell can observe visible light, because we can fully utilize the solar spectrum if we can observe the solar visible light region. And AM is the air mass to define the type of the solar spectrum. So if we move on to here, so AM can be defined by this 1 over cosine theta, and theta means the angle of this. So if the solar light is perpendicular to the earth level, then the AMX will become 1, because theta is 0, and thereby cosine 0 will be 1. And AM, in general, when we use solar spectrum to measure the efficiency of the solar cell, we usually use AM 1.5 as the regulation. And at AM 1.5, theta will be around 48.2 degrees. Then what is the AM0? As you can see here, AM0 is the dark light, which is the solar, the value in space, which means dark light. Okay, so let's think about the silicon solar cell. Basically, silicon has the energy band gap of 1.1 electron volt measured by people, and thereby if you look at the 1.1 electron volt, since we have to observe the solar light with the energy higher than the energy band gap, in the case of the silicon, we need to have the solar light in this region. Okay, so wavelengths can be converted into the energy based on this equation, because we have this, and depending on lambda, we can measure the energy. So energy will be proportional to the 1 over lambda here. So lower wavelengths generate higher energy, and 1.1 electron volt represent this in wavelengths. So if we observe this area, then the solar cell will not work. Okay, and this is about the mentioning. Then what if we have energy higher than energy band gap? Definitely, electron can be excited to the conduction band, but since we have higher than energy band gap, the electrons will be excited above the conduction band here, and then the extra energy, the difference between energy of the solar light and the energy band gap, will be lost in terms of the thermal energy. Okay, here. Okay, now there is a concept of the energy regarding the energy band gap. We can classify energy band gap into two different types depending on the shape of the energy diagram. So the first one is the direct energy band gap, and second one is the indirect band gap. So direct band gap is the band gap at the same momentum. So the energy band gap can be measured at the same momentum which is this, but indirect band gap can be defined by the band gap measured in different momentum, which is this. So some of the semiconductor can have the direct band gap, but some of them will have the indirect band gap. And what influence depending on the band gap type is, if a semiconductor has direct band gap, it will have strong absorption, while if it has indirect band gap, then it will have the weaker solar absorption ability. Okay, so for example, here there is a silicon. Basically, silicon has indirect band gap because the lowest energy level, which is conduction band, the momentum at the conduction band will be different from the momentum at the balance band. So on the other hand, the CIGS solar cell will have direct band gap and thereby very quickly absorb the solar cell as compared with the silicon with indirect band gap. Okay. Okay, so which means in this case we only need very thin layer to observe full amount of the solar light, while silicon will need a much thicker thicker part of the surface will be needed as a to fully absorb the solar light as compared with CIGS with direct band gap. Okay, now here. So in details, although this is explained here, but let me quickly explain this as well. So electron is observed. Okay, so the solar cell will observe the solar light, and then electron will be excited to the conduction band, and the electron in the conduction band will be moved to the lower energy level, which is N-type semiconductor. On the other hand, the hole will be transferred to the higher level energy level, which is P-type in the valence band. And transferred electrons will be circulated through the external circuit. Okay, here. And the energy difference in the conduction band or valence band between N-type and P-type will be defined by built-in voltage. Okay, here. Let me move on to the next slide. Okay, so if we measure, okay, so this is so I explained detailed mechanism of the solar cell, general solar cell previously, and then if we measure the solar cell by using solar spectrum, then we can obtain the following IV curve. So here I is the current or current density, and the V is the voltage. And usually when we use the dark light, which is AM0 solar spectrum, we will get this kind of curve. But if we use the solar light with AM 1.5 or 1, then we will have the following red line in curves in the IV figures. So based on these curves, we can measure the efficiency of the solar cell. Okay, so here, based on this, if we look at the red line, there are 3 points here. So the first one, which is this, is VOC, which is open circuit voltage. And open circuit voltage is the voltage when the current is not present, which is current is equal to 0. On the other hand, if we look at the y-axis, there is the ISC, which is short circuit current or short circuit current density. And this is the current density when the voltage is 0. Okay. So, and the third point is here, which is third point will be somewhere between these, depending on the square that we can make. So we can make the square with the maximum area, then like, let's say, okay, so if we measure the solar cell, we can usually we can usually obtain the following curve. And as I said, this is the short circuit current. And this is open circuit voltage. And you can easily make, depending on the point, we can make different squares. And at some point, the area of the square will be maximized. And that is the point that we need. And okay, here. So let's say this will be maximum point current, and this is maximum point voltage. Then the efficiency can be calculated by the equation here. So definitely efficiency will be the ratio of the generated power over inserted power. Okay. If let's imagine that we have 10 photons will be inserted into the solar cell based on the absorption, solar energy absorption of solar light. And let's imagine that we have 5 electrons are generated and can be used to generate electricity. Then the efficiency will be 50%, right? So that is the basic concept of the efficiency, and we can, if we look at this P out is measured by this area of the curve, which is I multiplied by V, maximum point. And FF, which is fill factor, has the definition of so that is the definition of the field factor. So that is why this relationship is satisfied, and based on this relationship we can make this final equation to measure the efficiency of the solar cell. Okay. And there is a concept of the superposition, and I want you to search for superposition and make some try to search for superposition, and this is sort of homework about this class. It is not like I don't expect multiple pages to explain superposition, but it is fine with one page or maybe half page, but I want to search for the superposition, and next time I expect the homework. Okay. And another concept that I'm going to explain is, okay, if you look at the slide, then you may be able to find some sort of concept of the superposition, but not only this slide, but also try to find out from internet. Okay. There is some sort of explanation on this superposition, but I want you to try to search for this concept with source from outside. Okay, here. Okay, so now let me move on to the details of the solar cell efficiency. So I explained this equation, which is efficiency, and this efficiency will be limited by several factors, which is field factor, short circuit current, and open circuit voltage. Because field factor, as you can see here, field factor can be defined by diode characteristic and the series resistance, which is intrinsic properties of the materials in the solar cell. And the second and third, open circuit voltage and short circuit current can be dependent on the band gap. So for example, if the band gap increases, then the short circuit current will be decreased, but the open circuit voltage will be increased. So when you consider this equation, VOC and ISC is at the same place, which is efficiency will be proportional to the short circuit current as well as the open circuit voltage, but the intrinsic characteristics of the short circuit current and open circuit voltage is on the opposite direction, which is one of them is increased, but the other one is decreased with band gap. So we need to be balanced between two concepts to maximize the efficiency of the solar cell. Okay, so the details here, but so based on those three limits, some of the people try to make kind of plots of the efficiency depending on the wavelengths or energy level. So these people try to identify the wavelengths. Okay, wavelengths. Let me try to. Okay, so they try to identify the band gap which allowed the cell to have the maximum efficiency, and they could find the maximum efficiency can be obtained in the 1.34 electron volt of the band gap. So this information is not present in this slide, so please memorize this. And okay, so almost done. So okay, so this slide explains the cost-related categories like high efficiency but high cost solar cell, like crystalline silicon or polycrystalline silicon. And the second category can be acceptable efficiency, but the solar energy materials are very low. Solar energy materials have the very low cost, like this kind of solar cells. And the last one is the concentration, but let me skip this one. So we can categorize in these two ways. So the first one is high efficiency, high cost. Second is acceptable efficiency but low cost. Okay, here this is just market-related information. So to summarize this introduction, as I said, light can be observed by the solar cell, and this absorption will generate excited electrons, and in the place of the electrons, hole will be generated. So electron-hole pairs are generated, and electron-hole pairs are also known as exciton. So here, electron is excited electron, which is the electron placed in the conduction band generated by the solar energy absorption, and the hole is placed in the valence band in the place of the original electron. Okay, and as I explained, the p-n junction, which is interface between p-type and n-type, will allow the electron-hole pairs to be separated. So this is sort of the driving force for the separation between the electron and hole pairs. I mentioned driving force. So the energy diagram in energy levels present in the p-n junction will be the driving force for the EH pair, electron-hole pairs. Okay. And okay, let me skip third one and fourth. The power out generated by the incident solar light will be defined by ISC, which is a solar circuit current multiplied by open circuit voltage and the field factor. And based on this information, and based on this, we could define the efficiency of the solar cell, right? This one. Okay, and the last one is just like cost related terms. So let me skip this. So yeah, this is the information that the author of the slide referred to. Okay. So that is the thing that we could learn. That is the last slide. Okay. 1 hour. Okay. So today we briefly learned about the solar cell, mainly focusing on the silicon-based semiconductor. Okay, so we are going to talk about the solar cell more in details in the next time. And yeah, that's it for today. Okay.